Hi class, welcome back to lectures on quantum mechanics. And again, our main reference for this lecture is Introduction to Quantum Mechanics by David J. Griffiths. And this book is recommended for you. So we'll start with, for this lecture, higher order degeneracy. So previously in the last lecture, we had double degeneracy. Now we'll take it to a higher level where the degeneracy is at least 3. So previously we have double degeneracy, and so we have represented the corrections by a 2x2 matrix, and this is represented by this matrix, where these matrix are just before we go there, alpha are just the contributions of the two states with the same energy, and E1 are the corrections of the energies, the eigenvalues of the matrix. So the WAA there will just be given by this. So you have phi I0 times operating on the perturbation, and then you also include in the integration the phi J0. So for the n-fold degeneracy, we should be able to construct n by n matrix with elements given by this. So to understand that fully, we'll go immediately to an example. So we consider the 3-dimensional infinite cubical well in problem 4.2, which can be found in the previous lecture. So the potential is V xyz of xyz is equal to 0 if x is between 0 and a, y is between 0 and a, and z is between 0 and a. So this is like a cube. Otherwise, the potential would be infinity. So the stationary states would be given by this, as we have shown. 2 over a of a square root of 2 over a sine nx pi over a times x for the x part, and for the y part you have square root of 2 over a sine of ny pi over a y, and then you have square root of 2 over a sine nz pi over a times z for the z part, where nx, ny, nz are positive numbers. The corresponding allowed energies, therefore, is just the sum for each contribution in the coordinates. So you have this E nx, ny, nz of 0, that's without perturbation yet. So you have pi square h bar square over 2 ma square times nx square plus ny square plus nz square. So in that case, for the ground state, you have nx equals ny equals nz equals 1. So you will have a non-degenerate ground state. This means that only one wave function has that energy. or only one wave function for the ground state. But for the first excited state, you have a triple degenerate energy. This means that there are three wave functions that share the same energy. So first you have phi 1, 1, 2, where here nx is equal to 1, ny is equal to 1, and nz is equal to 2. And for the second wave function, you have nx equal to 1, ny is equal to 2, and nz is equal to 1. And for the third one, you have nx equal to 2, ny equal to 1, and nz equal to 1. So you have there three wave functions that share the same energy. And the energy is just this one here. Or you can also write this as 6 pi square h bar square over 2 ma square, just to retain the 2 ma square below. So that's triply degenerate, meaning you have to get the corrections for each if there is a perturbation. So if we now introduce a perturbation, and this perturbation is given by h prime here, and where the perturbation is v sub o if x is between zero and a over 2, and y is between 0 and a over 2, otherwise it's 0. So therefore the potential is raised by an amount v sub o in 1/4 of the box. So here, this is your perturbation. So you have to calculate each E0, 1. So you will have here for the ground state, you will have this one. Now we're actually doing the correction for the first excited state, but let's look at this first for the first order correction of the ground state. So you have here E01, which is just given by this inner product, and using the wave function that we've seen in the previous slides, then we can get the correction, which is just 1/4 of V0. So here you have these terms you have to integrate with respect to z, y, and x. So in the first excited state, we have to use the matrix. We have to construct the matrix and then get the corrections. So in constructing the matrix, we use the definition of the elements, which is just given by this one, and to construct it, we have to get the elements, each element, I mean. So WAA, WBB, and WCC would have to be 1/4 V sub O, and it's just equal to this, equal to this one here. Because anyway you have for AA, you will have, of course, for AA, your wave function would be this part would be having the argument of the sine would be 2 pi over AZ, but again it will just give you the same as the integral here and here, and of course it will result to 1 over 4 v sub o. So you can do it in detail in your Google form for the assessment. And then WBB would also be the same, and WCC would be the same also, because anyway the arguments would just be transferring between x, y, and z. So we will now go to the off-diagonal elements, which are more interesting. So for WAB, so we have to deal with phi 112 and phi 121, and so here in this case, this one would be orthogonal functions, so they would have to give 0. However, this one will not give 0 because the limits would be from 0 to a over 2. Here in this, you're taking the whole thing from 0 to a. And finally, for WBC, you'll have to do this again. Be observant of the definition of the W. So in this case you have WBC, and so you have to be careful also with the integral. So none of the integrals is 0, and it will give you 16 over 9 pi squared v sub o. So you will have to have a constructed matrix W of this form. Where this is kappa is equal to 8 over 3 pi square, the whole thing square, and that's just equal to 0.7205. So in this case you will have to get the characteristic equation where you have to find the eigenvalues. So the eigenvalues here would be, here you would have to transform W. So you have to make this W minus identity times lambda equal to 0. You will have to get this would be alpha, beta, and gamma, and then you also have alpha, beta, and gamma here representing the wave functions. And then I'm sorry, this lambda would be W. So each W here would give you these values. So I have to still remember how to find the eigenvalues. It's just actually when you simplify this, this thing here, it would just be this 1 minus W 0 0 0 1 minus W kappa 0 kappa 1 minus W. This would just be equal to 0, and this would give you here this one. And the first order correction would be this here. So the energy level would have to be split into three energies. Here E10 is the common unperturbed energy, equation 6.34. That's here. So the perturbation lifts the degeneracy, splitting the unperturbed energy into three distinct energy levels. So you will have these three here. So there is no state in which it retains the original energy, but they're all being lifted a little bit. So if we say lambda is equal to 1, it would be here. But yeah, it's assumed that lambda here is equal to 1 for in the plot here, this lambda. So the good unperturbed states are linear combinations of the three wave functions. So you will have this original matrix here. You can get that by doing this. You have to multiply the original matrix that we got times the wave function, and that would just be the W times the alpha, beta, gamma, the contributions of each wave function. And then for each eigenvalue, you will have alpha equals 1. For W equals 1, you have alpha equals 1 and beta and gamma equals 0. So you will have this good, normalized good state. And for W1 plus minus omega, you will have alpha equals 0, but beta is just equal to plus minus gamma, which is just equal to 2 to the 1/2 or square root of 2, 1 over square root of 2 I mean. So you will have these two wave functions. So our wave functions and our energies have been corrected. So if you want to solve other problems. I can show you other problems you can solve in your spare time here. Class, by the way, if you cannot finish this lecture in one sitting, you can download this on your video and watch it even without internet connection. So we'll now go to the fine structure correction of hydrogen, because as you know, the energy levels of hydrogen are also degenerate. So for the hydrogen atom, the Hamiltonian is of course given by this. The first term is the kinetic term and the second term is the potential. It's the kinetic energy of the electron and plus the Coulombic potential energy between the proton and the electron. The motion of the nucleus is corrected by replacing m with the reduced mass earlier. This was found in lecture in chapter 5. So a more significant correction to the Bohr energies is the so-called fine structure, which is due to two distinct mechanism: relativistic correction and spin orbit coupling. And first we will discuss the relativistic correction before spin orbit coupling. So by the way, the fine structure correction is a tiny perturbation which is smaller by a factor of alpha square, where alpha here is given by given by this, and the expression would be this one, but this one is more important. This is a dimensionless factor, and this is called the fine structure constant. It's 1 over 137.036. Much smaller correction would be that of the Lamb shift, and of course the hyperfine splitting, and they are given by this hierarchy. So you have, of course, the Bohr energies would be in the order of lambda square mc square. M, there is the mass, of course, of the electron, and c is the speed of light. Then you have a fine structure correction of the order alpha to the fourth mc square. Lamb shift would be lambda to the 5 mc square, and hyperfine splitting would be in the order of this one. By the way, m over mp would just be the ratio of the mass of the electron and proton. By the way, the Lamb shift is associated with the quantization of the Coulomb field, and the hyperfine structure is due to the magnetic interaction between the dipole moments of the electron and proton. So you can also solve this problem later on if you have time. So let's go first with the relativistic correction of the energies of the hydrogen atom. But let's take a look at the Hamiltonian first. So the first term would be kinetic energy, and the kinetic energy is given by p squared over 2m, and by canonical substitution in quantum mechanics, your kinetic energy operator would look like this. However, your p over 2m is not relativistic, and you have to convert it to um, the relativistic formula. The kinetic energy is just equal to this term here. So that's equal to mc square over the factor, relativistic factor gamma overall, to be subtracted by mc square. By the way, this is the rest energy of the electron. By the way, the difference, the T here, is the energy that's attributed to the motion. So that's why it's the relativistic kinetic energy. But in terms of relativistic momentum, our momentum now would be written with the factor of gamma here. So that's gamma mv, because we're talking about relativistic motion in this case, so we have to have a relativistic p. So what will we do with this? So if we square p and multiply c squared, then add m squared c to the fourth, we will get this. And then of course we will get this term. That's just the kinetic energy plus mc square, the whole thing square, and we just have this one here as the kinetic energy. That is the relativistic equation for the kinetic energy, which could result to a classical one in the non-relativistic limit. So expanding in powers of the small number p over mc, we will have t equals mc square times this quantity here, and we expand that, we expand this. This one is just the classical kinetic energy. This one is the relativistic contribution to the Hamiltonian. And if we include that, that would be the relativistic correction, or the first order perturbation. I mean the largest term, relativistic term, in order to find the first order perturbation on the energy of the hydrogen atom. So in the first order perturbation theory, the correction to En is given by the expectation value of H prime in the unperturbed state. That's equation 6.9. So ER1 would just be the expectation value of HR prime, and that would be this one. And of course P, the momentum operator, is always Hermitian, so you can put it here, the P square. So now the Schrödinger equation for the unperturbed state says that P square phi is just equal to 2m times E minus V psi. So in general, our ER1 would be looking like this, as okay, as you can as you were able to calculate from here. So if you expand this term, you will have this one here. So for hydrogen, for which the potential is just equal to -1/4 pi epsilon sub O. So our ER1 would be equal to -1/2 mc square times the quantity En square plus 2En times this quantity E square over 4 pi epsilon sub O times the expectation of 1/r, and then you have this, and also times the expectation of 1/r square, where En there is the Bohr energy of the state in question. So it will depend, like En would be 1, 2, 3, and so on. So we'll now calculate the expectation value of 1/r. If we could go to 6.11, the problem 6.11 and problem 6.28, their expectation values would just be given by this and this one for 1/r square. So substituting them in equation 6.53 will give us this one here. And using the Bohr radius, we will be able to express everything in terms of ER1, in terms of En. So we have here this expression. So there are some notes here. Notice that the relativistic correction is smaller than En by a factor of En over mc square, which is approximately equal to 2 times 10 to the -5. Also, the non-degenerate perturbation theory is used in this calculation, even though the hydrogen atom is highly degenerate. But the perturbation theory is spherically symmetrical, so in terms of angular momentum, the L square and Lz will just commute due to spherical symmetry. Moreover, the eigenfunctions of these operators have distinct eigenvalues for the n square state with the given En. The wave functions phi and Lm are good states for this problem, hence the use of non-degenerate perturbation theory was okay. So you can solve these problems if you have spare time. So if you want to check problem 4.41, you can review the previous lectures. And of course, the other equations here are found in the previous lectures. So we'll now go to the second part of the correction, the spin orbit coupling. So if you could imagine the electron in orbit around the nucleus, and Yeah, basically we imagine the hydrogen atom to be having a heavy nucleus, which is the proton, and then the electron will just be revolving around it. It's orbiting around the proton, but from the electron's point of view, it is the proton that is revolving around it. So this is so this is the hydrogen atom from the electron's perspective. So it is the proton that is revolving around it, giving it an angular momentum L, and setting a magnetic field in the electron's frame. So since there is a charge that is revolving around it, so there's a magnetic field there, and of course an angular momentum is also measured at the center. So the orbiting positive charge sets up a magnetic field B in the electron frame, which exerts a torque on the spinning electron. It tends to align its magnetic moment mu along the direction of the field. The Hamiltonian is given by negative mu B, where mu is the magnetic moment, is given by this. If you still remember your university physics, you can solve for it. This is just the charge of the ring times the area that is enclosed by the ring of charge, and the period in which the current the period in which the charge revolves around the ring. So anyway, it's just actually the current times the area enclosed by the loop. So anyway, going back, the magnetic field of the proton is given by this, by Biot-Savart law. Here the I is just equal to electronic charge divided by the period which the charge revolves around the ring. On the other hand, the orbital angular momentum of the electron in the rest frame of the nucleus or of the proton is just equal to L equals the radius times mv, and that is equal to 2 pi mr squared over t, all over t. And also, as you can see in the figure, the magnetic field and the angular momentum is in the same direction, and they're related by this. So you can review some of your physics, but for the meantime you can just accept the things shown in here, but you can review your previous lectures in electromagnetism. And the magnetic dipole moment of a spinning charge is actually related to its spin angular momentum, and the proportionality factor is just the gyromagnetic ratio, which is taken in the previous videos of quantum mechanics, which you can also watch later if you forget about gyromagnetic ratio. So in classical electrodynamics, if you consider a charge Q smeared evenly around a ring of radius r, which rotates about the axis with period t, then our mu will just be given by this. So if the mass of the ring is m, its angular momentum is the moment of inertia times the angular velocity, which is just this one here. And the gyromagnetic ratio, which is now mu over s, is equal to q over 2m, and of course you can see from here that it's independent of r and t. So we can substitute that to our magnetic moment. So the direction of our magnetic moment in S is of course just the same, but if the charge is negative, it should be the opposite, so you have to put a negative sign there. So this is a purely classical result. However, it turns out that the electron's magnetic moment is twice the classical answer. So therefore, what exactly is our magnetic moment is given by this. So you can do some readings by how the factor 2, this factor here, disappears. So finally, our spin orbit Hamiltonian would be given by this. But if you can remember, we're dealing with the rest frame of the electron, and the electron is actually the one that's revolving around the proton. So the electron frame is not an inertial frame, because for one, it is revolving around the proton, and the direction of the motion is changing, so it is accelerating, so it's not an inertial frame. So the remedy is to make an appropriate kinematic correction known as the Thomas precession. You can also read more on this. And this throws in a factor of 1/2, such that the 4 here just becomes 8. So it would also be, so if we try to look at this one here, it would also be just taking the classical result, and the correction would just be this one. So as I've said, this is the spin-orbit interaction. Apart from the two corrections, the modified gyromagnetic ratio of the electron and the Thomas precession factor, they incidentally, they cancel each other. And it is attributable to the torque exerted on the magnetic dipole moment of the spinning electron by the magnetic field of a proton in the electron's instantaneous rest frame. So we'll now go to the quantum mechanics part of the analysis. So in the presence of the spin-orbit coupling, the Hamiltonian no longer commutes with L and S. So the spin and orbital angular momenta are not separately conserved. So you can check problem 6.14 later on. However, HSO prime does not commute with L square and S square and the total angular momentum. And you have here as a cons you have this one and of course this one as conserved quantities. So in this case, you cannot, you won't, well, you will have to use L square, S square, and J square, and JZ, because they're the good eigenstates for this problem. So you will not use now LZ and SZ, because they are not good states to use in this perturbation theory. Now, this is just some calculations, simple calculations of J square. So you can find J square is just equal to that. And of course, this one, LS is L dot S will just be 1/2 of this quantity. Therefore, the eigenvalues of LS are, as these are the eigenvalues of J square, L square, and S square. So for in this case, we're talking about an electron which is a fermion of spin 1/2. Meanwhile, the expectation value of 1 over r cubed, which could be solved later, is just equal to this one. And then of course our SO ESO1 would just be the expectation of HSO prime is given by this. So if we express this in terms of En, we will have this one here. So as you can see, the spin orbit coupling and the relativistic correction have the same order, is around the En square over mc square. So if we add them together, gives the complete fine structure formula. This is now this one here. And of course, En square would just be given by this one. And of course, if we get the Bohr formula, the grand result for the energy levels of the hydrogen, including the fine structure, would be this. So here you have N as the orbital number, and J is of course 1/2, 3/2, 5/2, 7/2, and so on. So these are the energy levels now being split by the J's here. For N equals 1, you have J equals 1/2, and for N equals 2, then you have J equals 1/2 and 3/2. So you must recall the previous lectures in order for you to understand this part here. So the fine structure breaks the degeneracy in L, that is, for a given N, the different allowed values of L do not carry the same energy. The energies are determined by N and J. The azimuthal eigenvalues for orbital and spin angular momentum, ml and ms, are no longer good quantum numbers. The stationary states are linear combinations of states with different values of these quantities. The good quantum numbers are n, l, s, j, and mj. So anyway, if you really want to delve more on this, you can read other books so as to understand more on this particular topic. Now, these are the problems that you can solve later on if you have time. Sorry. You can screenshot that. And of course, the next lecture would have to be Zeeman effect and hyperfine splitting. So that would be the third of this chapter. So I hope you've learned something about higher degeneracy, and of course about the corrections of the hydrogen energy. See you in the next lecture.